it occurred to me that I've never fully explained how the action of an algebraic group G on some tensor product of representations and of its Lie algebra are related. So I thought I'd just start out today just by kind of saying a little bit about that. So of course for the group, the way a group element acts on a tensor product of vectors, it's the diagonal action. Whereas for the Lie algebra, it's coming from the co-multiplication on the universal enveloping algebra. So the way a Lie algebra element acts on V tensor W, it acts on V plus acting on W. So I've already been using that quite freely, but let's just have a quick discussion of why it's true. There's a couple of ways to see it, actually. You can see it in the classical framework of differentiating in the setup that I set up in chapter 0, but just for a change, let me explain how to see it from the new point of view that I explained briefly last week from lecture, I think it was lecture 4.3. So in that lecture, remember I had this thing called dist-G, the algebra of distributions, which sat inside the full linear dual of the coordinate algebra. So it was all functions on the coordinate algebra which acted as 0 on sufficiently large powers of the maximal ideal associated to the point E. And then the Lie algebra G, then, in that point of view, that becomes identified with that maximal ideal M over its square, dual, sitting inside dist G in that way. So for this, dual coordinate algebra, this is an algebra with multiplication dual to the co-multiplication on the coordinate algebra, and this dist-G is a subalgebra for that natural multiplication, and the coordinate algebra of the group is also an algebra with its commutative multiplication, and the dual of that commutative multiplication doesn't work to give a co-multiplication on the full linear dual of the coordinate algebra. But as I explained before, it does restrict down to a well-defined co-multiplication on this sufficiently small subalgebra dist-G. So from this point of view, the co-multiplication on dist-G is the dual of the multiplication, that commutative multiplication on the coordinate algebra. And remember, I also explained that dist-G was isomorphic to the universal enveloping algebra in characteristic 0, but actually in characteristic P, you should forget about the universal enveloping algebra really and work with this algebra of distributions. It plays a substitute role for that. So this argument I'm explaining is totally fine in characteristic P as well, but you really need this distribution algebra in that case, which is no longer isomorphic to the universal enveloping algebra. Okay, so for this point of view, let's take some element x in the Lie algebra, and let's take a function in the coordinate algebra. So then you can write f as f evaluated at the identity. That's just a scalar multiple of the 1 in the coordinate algebra, plus some other function f prime, which actually lies in that maximal ideal. And then if you do that, x evaluated on f, so now I'm thinking of this x in the Lie algebra as being a function on me, which kills me squared. So So I'm just going to extend that to being a function on the whole coordinate algebra. That's this embedding here, so that it takes the unit element 1 in the coordinate algebra to 0. So then that means that x of f is just the same as x of f prime, which is in this ME, and x is 0 on functions in the square of that maximal ideal. So now we're trying to calculate the dual of the commutative multiplication on the coordinate algebra. So now we should take some other g. So let's take both f and g in the coordinate algebra. Then f times g, it's f of e plus this f prime, and similarly it's g of e plus g prime in that maximal ideal. And so that's what f of e, g of e, plus f prime g of e, plus f of e, g prime, plus f prime g prime. And this guy here, this is in that maximal ideal squared. So we deduce that x on fg, well, that's just a multiple of the identity element in the coordinate algebra, and x is 0 on that. And this is in the maximal ideal squared, so x is 0 on that. So it's just the same as x on this piece, but x on f prime is the same as x of f. And x on g prime is the same as x on g. And so there you see that this is just exactly x tensor 1 plus 1 tensor x evaluated on f tensor g, and then you have to, of course, contract the tensor product as usual. Okay, so it's x on f, and then this is the 1 in the distribution algebra, which acts on g so the co-unit on the distribution algebra, the unit on the distribution algebra, that's the same as the co-unit on the coordinate algebra, which is just evaluation at e. And so that's that term, and similarly 1 tensor x gives you that term, and this exactly shows that the delta of x formula exactly matches the dual map of the multiplication on the coordinate algebra. So from this point of view, that's exactly what you need to check, and maybe just to tie it up, right? So that's that formula for a Lie algebra element acting on a tensor product. To just tie it up finally with the diagonal group action, we should maybe note that this multiplication, the commutative multiplication on that coordinate algebra, is also the comorphism of the diagonal map from G to G cross G, sending a group element to the pair, diagonally embedded pair in that Cartesian product. And that's, of course, the map that you're seeing here in looking at the group acting on a tensor product. So both the group multiplication and the Lie algebra multiplication, they both come as duals of the commutative multiplication on the coordinate algebra. And that's exactly as it should be. Okay, so that was a bit of a digression, just to kind of go back to that stuff and do a little bit with it, which I hadn't really used before. What we were doing is we were talking about the representation theory of SL2. So let's go back to that and just wrap up that discussion. So we were looking at the Lie algebra SL2 of C, and we'd shown that the category rep G, that's finite dimensional G modules, or if you like, left modules over the universal enveloping algebra. We'd shown that that is a semi-simple abelian category. We'd classified the irreducible objects in that category, the irreducible modules, up to isomorphism in rep G. They were labelled by the natural numbers. So natural number n, I was denoting the irreducible up to isomorphism labeled by that n by just L of n. And so we'd seen how this was the irreducible highest weight module. Of highest weight n. So you remember weight meant the same thing as h eigenvalue. So H was this distinguished diagonal matrix in our Lie algebra G. Let me see, we had also identified L of n. We'd given a kind of natural realization of that irreducible. We did it in two different ways. One was as a quotient of those Verma modules, but maybe more natural is to get it as the nth symmetric power, where V here is the defining two-dimensional representation, the natural representation. If you remember, for the V, I just had the standard basis V1 and V2 for that guy. And so V1 was of weight 1, H acted as 1, V2 was of weight -1. And so under this identification, so of course the nth symmetric power has this basis of monomials. There's V1 to the power n, and then V1 to the n-1 V2, all the way down to V1, V2 to the n-1, V2 to the n. That's the monomial basis for that symmetric power. And the weights of those vectors, because V1 is of weight 1 and V2 is of weight -1, so then this V1 to the n is of weight n, and that was weight n-2, 2 minus n and minus n. And so that was just seeing again that this n, that's the highest weight. That vector V1 to the n is killed by the generator E of the Lie algebra G. That was what it meant to be a highest weight vector of weight n. So here I'm using, of course, that weights add when you take tensor product. I mean, if you have two pure tensors, two vectors, and you have a pure tensor V tensor W, and you act with H, it acts on V tensor W, or you act on W. So if V has weight lambda, and if W has weight mu, then this H on V gives you a lambda, and this H on W gives you a mu. And that should be a tensor product in there. Let's fix that. And so the weight of V tensor W is therefore lambda plus mu. That's the eigenvalue. That's what I mean when I say weights add under tensor product. So what I wanted to do, just to wrap this up today, is I wanted to think about the group G, the group SL2 of C. So, of course, that natural representation V of the Lie algebra, that lifts to a representation of the group. What I mean by that is that it comes that the G action is derived from the group action. That's kind of obvious in what we were doing in chapter 0. G is a closed subgroup of GLN, the Lie algebra is a closed subgroup of little GLN, and it was automatic in our constructions that the Lie algebra action was the derived action of the group action. But if V lifts, so does all these symmetric powers. That was my discussion at the beginning today. The diagonal action of the group derives to the action of the Lie algebra, this acting on each tensor and adding action that we're seeing for x. Okay, so the action of the Lie algebra on each of these symmetric powers, which is each of its irreducible representations, lifts to an action of the group. And if you remember, every finite dimensional representation is just isomorphic to a direct sum of copies of these guys. So we see that the action of the Lie algebra on any finite dimensional representation lifts to the group. So this shows that our functor from representations of the group to representations of the Lie algebra, which we constructed in chapter 0, this functor, which we already knew, is full and faithful. That was a question on the homework from last week. So this shows that this functor is actually dense. Every finite dimensional representation of the Lie algebra does come from a representation of the group. So this is an equivalence of categories. Actually, it shows even more than that. It actually shows that this is actually an isomorphism of categories. The action of the Lie algebra lifts to the group. So this functor is actually an isomorphism of categories. So you can simply identify representations of the group with finite dimensional representations of the Lie algebra SL2. So we've seen this, essentially we've seen this by brute force, right? We just classified all objects in this category downstairs and just see that the action of the Lie algebra comes from an action of the group on every single one of them. But this is something very special. We've just seen it for the Lie algebra SL2. It's true in general, you need the group to be semi-simple and simply connected over the complex numbers, and then this same behavior holds. But we know it's not true in general, even over the complex numbers, right? It's kind of false for. You don't have to look very far. It's already false for the multiplicative group, or indeed the additive group. So the group being semi-simple, it is part of this. You need the group to be simply connected as well. So let's maybe just remember what that's all about. So the group SL2 of C, that's the simply connected simple algebraic group with Lie algebra little SL2C. But there's another group there, PSL2, the projective special linear group with the same Lie algebra little SL2. That's, over the complex numbers, that's the quotient of SL2 by its center. And the center has this minus identity matrix in it. And already you see that the module V doesn't lift to PSL2 because minus the identity acts on V as -1. So this action of the group SL2 on its natural representation just doesn't descend to an action of PSL2 because the center doesn't act identically on it. In fact, for PSL2, you need these symmetric powers, you need n to be even. Only the even symmetric powers of those irreducibles give the irreducible representations of PSL2, not the odd ones. So somehow the group PSL2 only sees sort of half of the representation theory of SL2. That's why the words simply connected are in there. Let me just do one more example before we leave SL2 alone. So let's think about a tensor product. Let's take one of these irreducible representations, maybe L of 2 and L of 3. So This is the 3-dimensional irreducible and the 4-dimensional irreducible, and tensor them together. So this is a 12-dimensional module, and every finite dimensional representation of SL2 is completely reducible. So we should be able to decompose this into a direct sum of irreducibles. I want to show you how to do this. We've kind of already seen how important it is to use weights, eigenvalues for H, and so the point you should see from this is that indeed, once you know all the weights and all their multiplicities, all the dimensions of all the weight spaces, you have complete information. So let's just quickly go through it in this example and you'll see the general picture. So I'm just going to do a table here where I'm going to put L of 2 down the left and L of 3 along the top. So L of 2, it has weights 2, 0 and negative 2. And L of 3 has weights 3, 1, minus 1, minus 3. Weights add under tensor product. So this tensor L of 2 tensored L of 3, it has a basis whose weights are the sums of these 5, 3, 1, minus 1, 3, 1, minus 1, minus 3, 1, minus 1, minus 3, and minus 5. And so you see in particular that the 5 weight space in this tensor product is 1-dimensional. And that's the highest weight that you see there. So if you pick a non-zero vector of weight 5, it must be annihilated by E. So that vector will automatically be a highest weight vector. And so it's got to generate for us a copy of L of 5. So there must be an L of 5 constituent in there. But L of 5, the weights of L of 5 are 5, 3, 1, minus 1, minus 3, and minus 5. So that L of 5 will account for all of those weight spaces. And then when you factor out that L of 5, you're left with this 6-dimensional module. And the next highest weight in there is this 3-dimensional one. So there's got to be an L of 3 in there. And that L of 3 has weights 3, 1, minus 1, and minus 3. So if we factor that out, we've lost that next northeast strip of my rectangle. And then we're left with just a 2-dimensional module with the weights 1 and minus 1. That's got to be a copy of L of 1. And so you see that knowledge of the weights and their multiplicities determines the structure up to isomorphism. And our results about SL2 tell us exactly what the finite dimensional irreducibles are. They're the weights of these integers in these chains, and we know that H acts diagonally on the irreducibles. Since every SL2 module is a direct sum of those ones, H acts diagonally on any module. So this is kind of complete information, and you just look at this weight space decomposition. So this L of 2, its weights are 2. So let me write the answer. So let's look at this guy here. L of 5, L of 3, L of 1. L of 5 has weights 5, 3, 1, minus 1, minus 3, minus 5. That's its SL2 string. L of 3 is weights 3, 1, minus 1, minus 3. L of 1 is 1, minus 1. So in this tensor product, we see that, yes, the 5 weight space is 1-dimensional. I guess if I go to the explicit realization of these, this is the symmetric square of the natural module and the symmetric cube of the natural module. So then this 5 weight space, I can see exactly what it is. It's V1 squared tensor V1 cubed. That'll span that 5 weight space. And this is going to be exactly the highest weight vector in that copy of L of 5. That's summand L of 5 of this tensor product. And then we can move down, we can look at the 3 weight space. So part of that 3 weight space is going to come from that L of 5, but this tells us there's going to be another non-zero vector in here, which will be a highest weight vector in that L of 3. So what is the 3 weight space overall? It's 2-dimensional. I'm going to have what? V1, V2, tensor v1 cubed, or v1 squared tensor v1 squared v2. Those are the two monomials which will give a basis for that three-weight space. And if I wanted to locate that highest weight vector up to a non-zero scalar, I need to take a linear combination of these guys, and I need it to be killed by E to be highest weight vector. I think you have to take the difference. That'll be the highest weight vector in the L of 3. And then finally, if you want to get the highest weight vector in the L of 1, well, now the one weight space is three-dimensional. It'll be v2 squared tensor v1 cubed, or v1 v2 tensor v1 squared v2, or v1 squared tensor v1 v2 squared. That'll be the basis, and you'll have to take some linear combination to get the highest weight vector up to a non-zero scalar in that L of 1. And you see how there's some linear algebra problem to solve in order to work out exactly what the coefficients are. And, well, this is not super hard in this case, but even if you take a general finite dimensional irreducible of SL2 tensored another one, it's kind of a non-trivial problem to actually write down explicitly all of the highest weight vectors that this process tells you. So knowledge of weights and multiplicities only tells you the structure up to isomorphism, but there's often slightly deeper questions that you need to answer by doing more linear algebra to completely understand how this tensor product actually decomposes in practice. Okay, I think that's plenty of stuff talking about representation theory of SL2. Let's move on to the next topic. Actually, this is the final topic in this rather eclectic chapter. What I really want to do is I want to say more about nilpotent and solvable Lie algebras. Maybe a good place to start in chapter 0. We saw that every algebraic group is linear. So it was isomorphic to a closed subgroup of GLN. It's natural to wonder what happens for Lie algebras. What about finite dimensional Lie algebras? Is every finite dimensional Lie algebra isomorphic to a subalgebra of some GLN? And the answer to that is definitely yes. And this is a theorem, it's Ardo's theorem. So let's write that down just formally. Any finite dimensional Lie algebra, in fact over any field, doesn't have to be the complex numbers, is isomorphic to a subalgebra of GLV for some finite dimensional vector space V. So it's kind of exactly as you would expect, but actually the proof of Ardo's theorem is actually reasonably tricky. I think it was proved in, 1930, maybe 1938, it was around then, which is significantly later than most of the theory we're talking about. Most of this theory of Lie algebras was in place at the end of the 19th century. Work of Killing and Cartan was significantly earlier than Ardo's theorem. So that kind of points to the fact that this is actually a little bit of a stumbling point in the theory, is working out how to prove this. So that's a bit frustrating, because actually in all the situations that we care about for our purposes, there's not an issue here. Ardo's theorem is obvious for the Lie algebras G that we care about. What do I mean? I mean any Lie algebra always has its adjoint representation. It takes G to the general linear Lie algebra on the vector space G. And the kernel of this is what, sending x to add x, where add x is the endomorphism of G defined on Y by the Lie bracket. The kernel of add's just the center of the Lie algebra G, so this shows that any finite dimensional centerless Lie algebra is linear via the adjoint representation. So, for example, for a semi-simple Lie algebra, which is what we're mainly going to be interested in, that's certainly centerless. Every finite dimensional semi-simple Lie algebra is linear immediately, just by this adjoint representation. So, in that case, we really don't need Ardo's theorem, and maybe it's also worth remembering that all algebraic Lie algebras are linear. I mean, Lie algebras that are the Lie algebras of some algebraic group. So that's already known too. So I'm pointing those things out because I want to just justify the fact that I'm actually not going to bother proving Ardo's theorem. I'm going to skip the proof because it's it's more technical than we want at this point, given that actually we never need it. But it fits naturally into the development at this point. But so for a proof, let me just tell you where to look. You can look at there's a blog article by Tao, which you can Google to track it down, and he gives a nice exposition of the proof of Ardo's theorem. Actually, the way he does it, somehow the sticking point at the beginning is to deal with nilpotent Lie algebras. So he starts off very clearly by giving a proof of the following, which is the version of Ardo's theorem for nilpotent Lie algebras. Nilpotent Lie algebras are exactly where the adjoint representation kind of is useless here, right? Because a non-zero Lie algebra is nilpotent if and only if its center is non-zero, and then the quotient by the center is nilpotent too. So for nilpotent Lie algebras, you always have this center to deal with, so the adjoint representation is never going to help you in proving this linearity. Anyway, so in Tao's blog, he starts off with the proof of Ardo's theorem in the case of nilpotent Lie algebras. So here's the statement: if G is a finite dimensional nilpotent Lie algebra, then it is isomorphic to a subalgebra of GLV consisting of nilpotent endomorphisms of V for some finite dimensional V. Okay, so that's a sort of slight upgrade of Ardo's theorem in the case of nilpotent Lie algebras, because not only can you embed G into some GLV for some finite dimensional V, the G actually consists purely of nilpotent endomorphisms of that vector space V. Okay, so I'm not proving those things. In fact, we're not actually going to need to use either of those theorems in any significant way in anything that we're doing. But I do want to prove two much more classical theorems. So let me state these theorems today, and I'll prove them next time. Engel's theorem, which has to do with nilpotent Lie algebras, and Lie's theorem, which has to do with solvable Lie algebras. So here are the statements. Engel says, suppose you've got some linear Lie algebra for some finite dimensional vector space V, so say dim V is n, and assume that all elements of G are nilpotent endomorphisms of V. So that was exactly the conclusion of the nilpotent Lie algebra, the nilpotent version of Ardo's theorem. Any nilpotent Lie algebra can be realized as a subalgebra of GLV consisting of nilpotent endomorphisms. So any nilpotent Lie algebra in the setup of nilpotent Ardo there, it will give a situation where Engel's theorem applies. And the theorem says that there's a basis V1 through Vn for V such that G sends Vi into the span of all the strictly earlier vectors in the basis. So that's Engel. And Lie's theorem looks a little bit similar, so let's write down Lie's theorem at the same time so you can compare them. So again, G is a subalgebra, linear Lie algebra for some finite dimensional vector space V. And this time we assume that G is solvable. And then the conclusion is that there's a basis V1 up to Vn for V such that G sends Vi into the span of the weakly earlier vectors. So the proofs of these are going to come next time. But let me give a little bit of discussion just to finish up today. So once you've picked a basis, of course that identifies the general linear Lie algebra GLV with GLN of the field. And then Engel says that the Lie algebra G then, having made that identification, that G is identified with the subalgebra of GLN, which I'm going to call NN of C, the subalgebra of strictly upper triangular matrices. So in our ordered basis, elements of G send V1 to 0, they send V2 to a multiple of V1, they send the V3 to a multiple of V1 and V2, and so on. So you get strictly upper triangular matrices. That's NN of C. And Lie's theorem says that G embeds not into N but into Bn of C, the subalgebra of weakly upper triangular matrices. So matrices now where you can have stuff on the diagonal now. Okay, so anything strictly below the diagonal is 0, but stuff above the diagonal. That's Bn of C. So maybe you've done this exercise before, but you should note at this point that Nn of C is a nilpotent Lie algebra. And Bn of C is a solvable Lie algebra. And also the derived subalgebra of B is N. So if you combine Engel or Lie with the Ardo's theorem, well, actually you want Engel's theorem and the nilpotent version of Ardo, or Lie's theorem and the full version of Ardo. And when you do that, you deduce that any finite dimensional nilpotent Lie algebra embeds into Nn of C for some n, and conversely, and similarly, any finite dimensional solvable Lie algebra embeds into Bn of C for some n. So in other words, this Nn, this strictly upper triangular matrix Lie algebra, that's kind of the archetypical example of a nilpotent Lie algebra. And Bn of C, the weakly upper triangular matrices, that's the archetypical example of a solvable Lie algebra. Okay, so this is somehow the basic facts about nilpotent and solvable Lie algebras, at least over the complex numbers. Let me see. I think so. A corollary of Engel write it down. Such a Lie algebra G is nilpotent because the Lie algebra Nn of C is nilpotent. And corollary 2, actually I'm not going to fit that in there. Let me make a bit more room. Corollary 2. If G is a finite dimensional Lie algebra and add x from G to G is nilpotent for all x in G, well then G is nilpotent. That follows because, well, the kernel of add is the center, and the image of add, so that's G over the center, that will then be a subalgebra of GLG, all of whose elements consist of nilpotent endomorphisms by that hypothesis. And so Engel's theorem then implies that this G is then being embedded by this adjoint representation into the strictly upper triangular matrices, so it's nilpotent, as in corollary 1. Okay, so that's, anyway, so nilpotent Ardo plus Engel exactly give this statement: a finite dimensional nilpotent Lie algebra if and only if it's isomorphic to a subalgebra of Nn of C for some n. And Lie's theorem and Ardo's theorem give this analogous statement. For solvable, let's just maybe write down corollaries of Lie's theorem. If G is a finite dimensional solvable Lie algebra over C, then the derived subalgebra is nilpotent. I guess this needs Ardo's theorem as well to embed it into some GLV in the first place. That's my observation that the derived subalgebra of this Bn is Nn. And so if our G is embedded into Bn, its derived algebra is embedded into this nilpotent Lie algebra, Nn of C. And corollary 2, all irreducible representations of finite dimensional solvable G over the complex numbers, they're one-dimensional. That's immediate from Lie's theorem, right? Because the first vector in this basis, this will span a one-dimensional G submodule of any finite dimensional representation V. It's worth thinking about both examples, both theorems with the example of the Lie algebra SL2 of K for K of characteristic 2. Engel's theorem is actually true for any field, just as Ardo's theorem is true for any field. Engel's theorem, it doesn't need to be algebraically closed or of characteristic 0. So everything I've said so far about Engel is true in general. The finite dimensional nilpotent Lie algebra can be embedded into this strictly upper triangular matrix Lie algebra over any field. But, of course, to do that, SL2, it's already embedded in matrices, and in characteristic 2, this is actually a nilpotent Lie algebra. But there's no such basis for the two-dimensional representation K2 for SL2 of K. You have to actually change the representation in order to achieve the conclusion of Engel's theorem, because SL2 of K, these are not nilpotent matrices in there, so the hypotheses aren't satisfied for that defining representation of SL2. Lie's theorem, on the other hand, requires that the ground field is of characteristic 0 and algebraically closed. So again, SL2 of K gives you a counterexample because the defining representation of SL2 of K is actually an irreducible representation for that Lie algebra, even though that's actually a nilpotent Lie algebra. So this is kind of just useful to think about that, to give yourselves counterexamples to Engel's theorem. If I tried to state Engel's theorem in the same way as I stated Lie's theorem, when I simply said here if G is solvable, if for Engel you just said and G is nilpotent, that would be a false statement, because here's a nilpotent Lie algebra, but the defining representation of that has no such basis. Engel's theorem is actually valid over any field. But Lie's theorem, and you'll see in the proof next time, we require characteristic 0 and algebraically closed. And again, take SL2 in characteristic 2 to get a counterexample for Lie's theorem if you're in positive characteristic. Okay, so that's set it all up. We've got to prove those two theorems next time.